Welcome to Center of Math's problem of the week. For this week's problem, we have a function f defined on non-negative integers whose codomain is also the non-negative integers, and which satisfies f of n plus f of n equals f of m plus f of n. Yeah, f of m plus f of n equals f of m plus f of n. And this is valid for all non-negative integers m and n, and we want to find all such functions f that satisfy this. So we're working with this functional equations. We're working with only non-negative integers. So the first thing we can do is just plug in 0 everywhere. So f of 0 plus f of 0 equals f of 0 plus f of 0. The thing on the left is just f of 0. So we're going to subtract off these two f of zeros, and we're left with 0 equals f of 0, which is simple enough. So the next thing we can do So we just plug in m equals 0. This becomes f of n. F of 0 is just f of 0, which is just 0. And f of n stays f of n, and we're left with f of n equals f of n. So this is another tidbit of information. Now, another thing we can do, we can plug in, for m here, we're going to substitute m plus f of n. So we're going to try to find out what m plus 2f of n will give us. So note, because we know f of n equals f of n, that f of m here, we can just write that as f of m. This simplifies this equation a little bit. So substituting m plus f of n for m here, we're saying m to m plus f of n. So f of m plus 2 f of n equals f of m plus f of n. F of m plus f of n plus f of n. F of m plus f of n from our original functional equation is just f of m plus f of n. So this is equal to f of m plus 2f of n. So f of m plus 2f of n equals f of m plus 2f of n. So we can kind of, it's a little bit linear. Yeah, so we can do this repeatedly. We'll get if we keep plugging in m plus f of n for m here, this will become m plus 3n, m plus 4n, etc. So in general, m plus k f of n equals f of m plus k f of n, where k is some non-negative integer. And so this is another little bit of information. Now we can do another thing. Another thing we can do, we can plug in m minus f of n, or m here, being careful that this m minus f of n is greater than or equal to 0, because we still want to be in the non-negative integers where this is defined. So doing that, we get f of m equals f of m minus f of n plus f of n. If we subtract off f of n from both sides, we get f of m minus f of n equals f of m minus f of n. And note, if we keep repeating the substitution, saying m to m minus f of n, this becomes m minus 2 f of n. M here is f of m minus f of n, which is, we can use this to get it. That's equal to f of m minus f of n minus f of n, or f of m minus 2 f of n. And we repeat this to get, in general, f of m minus k f of n equals f of m minus k f of n. And so we know now k can in fact be positive or negative integers from what we learned previously. So from these two bits, we can do another thing. So so with our equation here, instead of m, we can write f of m. It doesn't change anything because f of m is just f of m. And then we recall we can, for f of m, f of n, we can repeatedly add or subtract f of n's, f of m's to this to get a form k1 f of n plus k2 f of n. And this will be equal to the same thing, k1 f of n plus k2 f of n, from where k1 and k2 are just integers, and from what we previously learned, these can be integers, and this will stay a fixed point of our function. And so it's a common known fact that, so we take any two integers in the range, non-negative integers in the range of f, and so we can get that their greatest common divisor is in fact a fixed point of f. And also note that just saying when these k is equal to 0, we have f of k times f of n equals k f of n. And here, because we can do this, we can say really the range, there is some integer d that divides every number, every integer in the range of this function. Because if there wasn't, if there's some integer that did not divide d, we can do this, we could find out what their greatest common divisor is, and then that integer would be something that divides every number in the range of f. So we have some number d that divides every number. And we also note that, so if f of n is equal to this d, because d is clearly going to be in our range, any multiple of d is a fixed point. And because every point in our range is divisible by d, our range is really just multiples of d, just some integer d. And so now we're almost done. So now we pick some non-negative integer d. We pick some non-negative integer, some positive integer d, and we consider all L greater than or equal to 0, less than d. And we know f of L, we can write any integer as L plus RD, where L is less than d by division algorithm. So f of L plus RD is f of L plus R f of d, because d is a fixed point. And this is just f of L plus RD. And f of L must be divisible by d, so f of L is just some g of L d plus RD, which is divisible by d, is such a fixed point of our function. And this describes all our functions. We pick some integer d, we can send everything to 0, d can be 1, d can be 2. So that if we have any integer, we represent m plus L plus RD. This integer will be sent to g of L d plus RD. So we pick some integer d, we assign some values g of L for L less than d, greater than or equal to 0, and that will define all our values for every non-negative integer. And we can plug this back into our original functional equation, and you'll see that, in fact, both sides will equal to each other. And we just showed that it has to be of this form. Thanks for watching. Please check us out on math.org, check out our blog, and follow us on Facebook and Twitter. Thank you.